Welcome back to Physics Fundamentals. In this video, I want to talk about simple harmonic motion. The title Simple Harmonic Motion sounds a little bit intimidating until you take the time to digest what exactly we are talking about. Most important in this name is we're dealing with simple harmonic motion. In physics, whenever we're talking about a simple anything, we're generally talking about some tool that we have used to idealize the situation we're studying. So in the case of simple harmonic motion, the simple of it is going to idealize that no odd effects are going to come in. And then harmonic is a term that we throw around a lot in mathematics and in physics. Something is harmonic if it repeats. So we are looking at motion that repeats, and we're going to make our model as simple as possible. There are a couple of classic examples of how to treat simple harmonic motion. Probably the most common is a spring. Springs are so incredibly important in the study of physics because at a certain level, everything is a spring. If you have something and it has some elasticity to it, you push on it, it gives, and then it bounces back to where it was. Mathematically, we can describe that behavior as the behavior of a spring. And when we are working with a spring, we have this nice behavior where when you put a mass on a spring, it is going to bounce. Eventually, it will reach this center of oscillation, and if I grab this and try to settle it down a little bit, I can get it to more or less stay in one place without any issues. But if it's not there yet, right? If I release it from far away from that nice stable position, it's going to bounce back and forth. And here I have a trace coming in and showing us how it is going to bounce. All right, let's pause this, get rid of that mass. There are two things that affect the way that a spring is going to bounce. The first one is how much mass has been applied. So over here I have a mass that's known, 100 grams, and a couple of unknown ones. Let's go ahead and put the 100-gram mass on. And I'm going to start it way up here because that's a consistent place where I can start it. It's going to give it a very large period of motion. And there it goes. It's bouncing pretty rapidly. Some things that I can do that will change how rapidly it's bouncing. I have a control here that will change the mass. If I suddenly increase the mass, the interesting thing that happens is that, well, the distance that it's bouncing has actually increased, but the time between has gone down. And if I go ahead and decrease this mass, we get just the opposite, right? The distance that the mass is bouncing has become a lot smaller, but it is also going a lot faster. All right, let's find a nice happy medium here, something like that. That looks pretty nice to deal with. The other thing that I can change is the strength of the material of the spring. We very simply call this the spring constant, and if we have a smaller spring constant, it's going to cause the distance that the mass is bouncing to increase, but the time between to slow down. And if we have a very high spring constant, again, the opposite will occur. So those two behaviors kind of in lockstep working against each other. Just something worth having in our back pocket. Right? If I jump back over to my notes page, we're going to describe this whole interaction in terms of the period. All right, so the period of a harmonic oscillator, something that is moving according to simple harmonic motion, is the time it takes to repeat the state. And when I say the state here, I mean same position and the same velocity. And when I use the word velocity here, remember that's the vector form of speed. So I'm talking about the magnitude and the direction. All right, so if I jump back over to my model here, right, notice on the center point, we're going through that a couple of times in the line that's drawn, right? It starts drawing the line as the mass goes through that center point, continues down, continues all the way back up. When it passes through the center point on the way back up, it's going in the other direction. So it is not the same velocity. The period doesn't end until it's coming back down. All right, so down, up, and back to center is one period. Down, up, and back to center is one period of oscillation for our mass on a spring. The variable that we use to represent period tends to be a capital T. Right? It is a time, so we want to use T, but we want to be able to talk about the time duration as well, so we want to use a different letter. We just got done using T to represent temperature. We're not going to be talking about period and temperature at the same time, so that shouldn't be an issue. But I did want to at least briefly mention that some sources like using the Greek letter tau. It's kind of pi, but with only one leg. And it's just another thing that kind of looks like a T. So you'll see that sometimes if you're looking at sources other than our textbook, other than these videos. But the period of oscillation is given by 2 times pi times the square root of m over k, where m is the mass attached to the end of the spring, and k is the spring constant. All right, so spring constant is a property of material. The type of material that the spring is made of will affect the spring constant. The size of the spring will affect the spring constant in every way possible, right? So if the coil of the spring is made of thicker wire, that will change the spring constant. If the coils are wrapped in a wider loop or in a tighter loop, that will change the spring constant. How much the spring likes to be stretched in its natural state will change the spring constant. How tall the spring is will change the spring constant. All right, so there are a lot of control variables in creating a spring that will affect the spring constant. All of that gets wrapped up in a nice bow, placed into one number that we can use pretty readily. The units of the spring constant are almost always given in newtons per meter. So if we think about the dimensional analysis, all right, so if I consider an example where I have a mass of, let's say, 0.200 kilograms, right, the 200-gram mass that I was just looking at, and the material I'm looking at has a particular spring constant of, let's say, 0.500, newtons per meter, well then T equals 2 pi times the square root of 0.200 kilograms over 0.500 newtons per meter. Most of this I can just take care of with the calculator, no big deal. Right? 2 times pi times the square root of 0.200 divided by 0.500. Numerically, this is going to come out on the order of 3.97. And then let's think about the units. Right? Underneath the square root, we've got kilograms in the numerator. We've got newtons per meter in the denominator. Well, a newton is a kilogram meter per second squared. And then we've got 1 over meter. So the meters are going to cancel each other out. And then the kilograms are going to cancel each other out. So I've got left 1 over second squared. And the reciprocal of a number is just that number. So this is the square root of second squared. And the square root of second squared is just seconds. All right, so going off to the side here, we can work through the units. It should make sense, right? If we are dealing with if we're dealing with something that should be measured in time, it makes sense to us that the result comes out in seconds, but it's always worth double checking, right? Whenever you're introduced to a new formula, going and looking at the formula, looking at the units and making sure that everything works out fine is never a bad place to start. All right, so that's a spring. That's one of the two simple harmonic oscillators that I wanted to look at. The other one is a pendulum. So here we have a simulation where I do have two pendulums. It's hard to see because they're kind of sitting on top of each other. But at the moment, I have two identical pendulums. They have the same mass, they have the same length, and they're just attached to this pivot point up here and able to swing back and forth. Right now, I'm currently grabbing onto this one and causing it to swing on my own. But if I let go of it, it will swing in its natural state. And I've got this nice thing tracing out the period. Just like with the spring, the period here is going to be through the center, over, back, and to where it started. So that not only is the position the same, but it's traveling in the same direction. All right. So if I have these two pendulums that are both the same length and the same mass, and I put them at the same position and I let them go, it shouldn't be a surprise that they trace out exactly the same path. That's not the interesting question here. The interesting question is, what if I change things around? Let's say I take this pendulum, this light blue color, and I'll put it at 10 degrees. And then I'll take the yellow pendulum, and I'm going to put that at 16 degrees. And when I let these two pendulums go in this orientation, what I want you to notice is that they're following the same sort of a trajectory. The blue pendulum is not going nearly as far as the yellow pendulum is going, but they're moving at exactly the same rate, right? They both have the same amount of time to complete one period. That's a very interesting property of pendula. The period of the pendulum depends on the length of the string, and that's really it. So if I take one of these pendula and I shrink it down, oops, that's not the one I want to change, that's the one I want to change. All right, so I've got these two pendula that have a very different mass. And let's again set it up so that they're starting at the same angle. And changing the mass hasn't changed anything. They're still following the exact same trajectory. Just to make sure, let's go ahead and set them back to having the same mass so that that's not something that we have to worry about. And let's change the length of the strings. Oops. Let's make this string a little bit shorter, and let's make that string a little bit longer. And once again, I'll do the same thing. I'm going to pull them back to exactly the same position and let them go. And when I do this, they immediately fall out of sync with each other. They are no longer moving at the same rate. So the length of the pendulum is going to change the period. And that's it. That's the only thing that really matters. So if I jump back to my notes here, I can write out that for a pendulum, the period is 2 pi times the square root of L divided by G, where L is the length of the pendulum. All right, so it's the distance between the point where it's pivoting and the center of mass of the bob at the end of the pendulum. And then G is gravitational acceleration, 9.8 meters per square second. And that's all we need. Once again, the units will work out. All right, so let's say that we have a particular pendulum. One of the ones that we were just looking at had a length of 0.80 meters. So if I plug those things in, sure, we can do the calculation. 2 times pi times the square root of 0.80 divided by 9.80. My calculator tells me comes out at 1. I'll give it 3 significant digits, 1.80. Technically, we only have 2 there, but it's fine. And then the units. Well, we've got meters over meter per square second. And the meters are going to cancel each other out, leaving us with 1 over second squared, which is again square root of second squared, and square root of second squared is seconds. So once again, the units work exactly the way that we think they should. All right. There is so much that we can do to talk about the properties of pendulums, the properties of springs, or harmonic motion in general. But I think for right now, that's probably good enough. So I'll wrap up the video with that. As always, thank you for joining me, and I'll see you next time.